Good evening, I'm Brian Greene. In April 1919, a 34-year-old German mathematician was in his study, sitting at his desk. His 9-year-old son was on the couch, where he'd often be when his dad was working. And Theodor Kaluza was there at his desk, doing calculations as he often would, when all of a sudden, he opened his eyes wide. He slammed the desk with his hands, he shot to his feet, and he began to sing an aria from Figaro. Dum, dum, da, da, dum, dum. The program here tonight will explore what it was that Theodor Kaluza was singing about. He had found the possibility that there was reason to believe that our universe might have more than the 3 dimensions of everyday space that we all know about. And the program that we'll be discussing here tonight will follow the variations on that theme that have rippled through physics over the last 8 decades, and we'll discuss where our thinking is today on this possibility of more dimensions than meet the eye. Now, to give you a sense of where this idea came from, where Kaluza's thinking came from, we need to take a step back and think about certain physics, certain discoveries due to Albert Einstein that were the precursor to Kaluza's thinking. To do that, we need to think back to roughly the year 1907. 1907 was a time when Einstein was really basking in the glow of having already discovered what we call the special theory of relativity, material that we'll touch on a little later tonight, various insights into nature of space and time, and he set himself around that time the goal of understanding an even bigger mystery, the force of gravity. Now, you need to know, around 1907, in fact, way before that, many physicists believed that gravity was pretty much understood from the work of Isaac Newton. However, Einstein was, of course, the kind of thinker for whom there was no such thing as received wisdom that he wasn't willing to challenge, willing to think through in fresh, new ways. And in particular, when he was thinking about the force of gravity that everybody was aware of and thought that we understood well, he asked a very simple and basic question that no one seemed to have the answer to. And that question was, how does gravity really work? How is it that one object in the universe, like the sun, can somehow exert a pull on another object like the earth, even though there's nothing connecting them? There's effectively empty space between them. How does gravity get the job done? So naturally, to try to answer that question, Einstein went to the Principia, Newton's Principia, which has all the results in math and physics that Newton found in his lifetime. You know, it was the book that was required reading for tonight's discussion in, of course, the original Latin. Now, of course, you know, most of you therefore know the story, but for the 1 or 2 who maybe didn't quite finish the reading, let me just carry on. So Einstein went over to the Principia. He opens it up to letter G, finds the law of gravity that Newton had written down in the late 1600s, and then he goes a little further to the subheading M for the mechanism by which gravity operates. And there Einstein finds something surprising because Newton basically says, I don't know how gravity works. I've been able to write down an equation that seems to govern its influence, but if you ask me how it actually gets the job done, I don't know. In fact, in his own words, he said, to the answer of that important question, the mechanism by which gravity operates, Newton said, I leave it to the consideration of the reader. Most readers at that point would simply read on. Here is where Einstein was different. He spent 10 long years trying to figure out how gravity works, and he finally did come to the answer with his so-called general theory of relativity. And let me just quickly describe to you what he found, because it sets the stage for this idea of there possibly being more than 3 dimensions of space. How does it go? What's Einstein's idea? Well, the idea is often described in a metaphor that you perhaps have heard before. Let me describe it and then I'll show you a visual. Forget about the universe and gravity for a moment. Instead, imagine that I have a big rubber sheet stretched nice and taut in front of me. In your mind's eye, you can watch a marble as it rolls across the surface of that rubber sheet. It goes in a straight line trajectory, nothing too weird about it. But now if I change things a little bit, I put a rock on the rubber sheet. Now the sheet looks like this. It's warped, it's curved, it's deformed. If I take that same marble, it won't go in the same straight line trajectory any longer. Now it will go in a curved trajectory because it's rolling on the curved surface of the sheet. Einstein says, take that idea and apply it to the universe, the fabric of space. Not a rubber sheet, but the fabric of space. And what would that look like? It would look like this. So if we go out into the cosmos and use this as a representation of 3-dimensional space, which is a little hard to work with, so let me do what we'll often do tonight, go to a 2-dimensional analog that we can picture better. Space, like the rubber sheet, is nice and flat when nothing is there, but if the sun appears, the fabric of space curves. Similarly, in the vicinity of the Earth, the fabric of space curves. And now focus your attention on the moon because this is the main point. The moon is kept in orbit because it's rolling along a valley in the curved environment that the Earth creates. That, Einstein says, is how gravity is communicated from place to place. Warps and curves in the fabric of space. The Earth, too, kept in orbit because it is rolling along a valley in a curved environment that the sun creates. That is how gravity works. Now, Kaluza got wind of this idea, as did the whole scientific community. But Kaluza, when he heard of this idea, began to think. He said, look, if Einstein had this tremendous success by describing the force of gravity in terms of warps and curves in space, and in fact, space and time, as we'll talk about later, maybe I can play the same game and describe another force of nature in a similar language. Maybe put them together. Because at the time, gravity was one force, but another force was the electromagnetic force. So Kaluza said, what if gravity is warps and curves, and the electromagnetic force is also warps and curves? The problem was, warps and curves in what? Einstein had used up space and time. There didn't seem to be anything else to warp and curve. So Kaluza said to himself, what if there are more dimensions of space than we know about? What if there's one more dimension of space? So what he did, what he was doing at his desk was he took Einstein's equations that were derived and formulated in the context of 3 dimensions of space and 1 of time. He said, what if there are 4 dimensions of space and 1 of time? He writes down the equations, and here's what he finds. He finds some of the new equations to be exactly the ones that Einstein had for 3 dimensions and 1 of time. But because he had an additional dimension of space, he had an additional equation. And when he looked at what that equation was, it was exactly the equation that Maxwell had written down years before for the electromagnetic force. Wow. He found, and what made him so excited was that he had put gravity and electromagnetism together by imagining that there was one more dimension of space that for some reason we don't see. Now that was the small detail. If there is an additional dimension of space, where is it? Why don't we see it? Now Kaluza himself didn't really have an answer for that, but in 1926, Oscar Klein suggested an interesting possibility. He said, look, maybe dimensions come in 2 flavors, 2 varieties. There, say, is the big variety that we can easily see, left, right, back, forth, up, down, but maybe there are additional dimensions that are curled up, really tiny, and they're so small that they're all around us, but we can't see them. Maybe that's where there could be additional dimensions of space. What would that look like? So just to get a sense of that, this little analogy looks at a traffic light supported by a cable. From a distant vantage point, the cable looks one-dimensional because we don't have the visual acuity to see the circular part that wraps around the cable. But if we zoom in and take the perspective of a little ant, the ant is so small that it can walk along the cable, but can also walk around the cable. And I do hope you appreciate this visual because it took so long to get these ants to do this. But there you have it. A dimension that's small can be difficult to see compared to big dimensions that are far more obvious. Now, that, of course, is just an analogy. What would that look like not for an object in space like the cable, but rather space itself? So let's take a look at that. So the idea would be this. Here is three-dimensional space. I can only put two on the screen. If we go smaller and smaller and smaller, the idea would be that if you go small enough, you can encounter additional spatial dimensions. Anything not in the grid are dimensions that we can't see. Additional dimensions that are curled up. If you have a really ultra-microscopic ant down there, it can walk in the grid part, the part that you and I know about, but the ant is so tiny that it can walk around these curled up dimensions that you and I just are not aware of because they're too small. They're all around us, but they are just too small. That was the idea. Now that was 1926. Einstein himself got very excited about this idea, began to work on it. The problem was when people started to analyze this in detail, this possibility of extra dimensions in greater detail, they found insurmountable problems. They couldn't get the electron to fit into the theory in the right way, all sorts of problems of detail of that sort, and ultimately the idea was dropped by the 1940s or so. Interesting idea, it basically went away. Until something quite dramatic happened in the 1980s. In the 1980s, people began to pick up the trail that Einstein had left off in 1955, the search for unified theories, much as Kalutza's work was trying to put gravity and electromagnetism together. Physicists took up that charge once again with various theories that you'll hear something about tonight, supersymmetry, and one in particular called string theory. And in string theory, the idea of extra dimensions comes roaring back. So just to give you a feel for what these ideas are, if we just take a quick look here, string theory tries to answer the question, what are things made of? So if we take that teapot, we zoom inside of it, you all know that if you go sufficiently deeply, you'll get molecules and atoms. Of course, we all know that atoms themselves are made up of particles, electrons, swarming around a nucleus, neutrons and protons. Inside the neutrons and protons are smaller particles called quarks. This is where the conventional story of matter stops. The new idea, completely hypothetical, of string theory is that you can go at least one level further. Inside these particles, as you see, according to the theory, would be little vibrating strings. And the different vibrational patterns of these little tiny strings would give rise to the different kinds of particles in the world around us. So if these ideas are correct, and we do not know if they are, but if they are correct, this would be what the microscopic makeup of matter would look like. Little tiny vibrating filaments. And I bring up this idea because when scientists started to analyze the mathematics of string theory, they found certain equations that could only make sense. The theory would only be internally mathematically consistent if the universe had more than 3 dimensions. In Kalutza's day, he just had this creative idea of the possibility of an additional dimension of space, but it wasn't something that was forced upon him by the mathematics. String theorists have found quite the opposite. In studying the mathematical equations of the theory, the possibility of extra dimensions is forced upon us. The theory just doesn't make sense without them. And in fact, the extra dimensions, not just one in number, the way it was in Kalutza's day, but depending exactly on how you count, 6 or 7 additional dimensions of space that themselves have a very interesting and rich geometry. Let me just show you what they would look like. So picking it up from that little ant with the example of an additional dimension in the shape of a tiny circle, string theory says, no, the additional dimension wouldn't look like a tiny circle. Instead, it says that the additional dimensions would look kind of like this. These are called Calabi-Yau shapes. We'll encounter them in the discussion that we'll have in a little while. These are complex scalar manifolds of vanishing first Chern class, but if that language offends you, you can just look at the picture. And you see that there's this nice, rich, intertwined geometry associated with these additional dimensions. And, if these ideas are correct and you're able to magnify the microscopic fibers of space all around you, not deep out in the cosmos, but right here in this room, if these ideas are correct and you magnified space, you'd see the ordinary dimensions that we all know about, the grid, but you'd also see those little tiny curled up dimensions, additional dimensions of space that the mathematics absolutely requires. Now, we do not know if these ideas are correct. We are still struggling to figure out whether they are right or not. But we seem to see a pattern. The pattern seems to be that when we try to find the deep laws of the universe, the mathematics seems to be searching for more space. It seems to be spreading and sprawling, stretching and straining. It's as if the mathematics, much like Beethoven's Grosse Fuge, is bursting at the seams.
Pressure Quartet. I also want to thank Eugene Drucker of the Emerson Quartet for suggesting that piece of music to begin to suggest the dimensionality, the interconnectedness of those various themes. Did you hear it? Yeah. Yep. Did you see both the complexity and the simplicity sort of living together in tension and release? An artist brings us that, and of course, talking about multidimensionality, Beethoven wrote that when he was completely deaf. So imagining all of that from a space inside the mind. Talk about crossing dimensions. I'm John Hockenberry. I'm your moderator for the rest of this adventure. The World Science Festival, all about science, the original exploration, except we all are aboard for the ride. We're all a part of this festival, and I think that's part of what we're going to explore here. But multidimensionality, really? Seriously. This is a stretch? It's Saturday night in New York. How many of you believe that the three dimensions, line 1, 2, and 3 are all we get? Clap if, well, of course, why would you be here if you believe that? Yes, consider. So how many people believe they've seen evidence of dimensions beyond the 3 that we understand as spatial dimensions? Clap. Clap. Yeah, right. Don't laugh. How many people are currently occupying a different dimension beyond the 3? Yeah. Well, I want to poll the audience because I want the panelists who come out who think that they're dealing with an arcane sort of subject that's way off in the lofty clouds and doesn't connect with people. They understand they're dealing with a sophisticated group here tonight. Multidimensionality is nothing new, but there is a need, a sense, a passion that we all have for understanding beyond what is our senses. Our senses are fantastic, and certainly Beethoven understood that. Losing his hearing was a real setback. But the idea that you would go beyond your senses to create art and to describe the world that we live in is really what this quest to understand multidimensions is all about. And as Brian tells us, it's a very powerful idea in terms of describing physics, but it's a powerful idea that has a lot to do with the way we live in the world beyond simply physics. And there's nothing simple about physics, as you'll discover tonight. So we have an amazing panel to explore this idea with, and I want to welcome them. I also just want to say, you saw the video, right? The stoplight metaphor there, the ants. We see the cable as a line, the ants see it as a circle. I mean, wouldn't you love to have been in the room when Brian Greene told some grad students to go out and shoot ants? That street corner. I mean, I just, this is what the festival is all about to me, moments like that. So, please, let's begin. Joining us from the Arizona State University is Lawrence Krauss, Foundation Professor of Earth and Space Exploration and Director of the ASU Origins Project at Arizona State University. Very familiar face here at the World Science Festival. He's just completed a scientific biography of Richard Feynman, and of course his work addresses the intersection of cosmology, and elementary particle physics, and many other questions about the origin of the universe. Larry, thanks for being here. Please welcome Linda Dalrymple Henderson, who is an acknowledged expert on the history of modern artists' engagement on the issue of multidimensionality. She is the David Bruton Jr. Centennial Professor in Art History and Regents Outstanding Teaching Professor at the University of Texas at Austin. Linda, thanks so much for being here. Shamit Khatru is an award-winning physicist. He's an expert in string theory. He is professor of physics at Stanford University and has made central contributions to the string theory of extra dimensions. Shamit. And of course, we couldn't do it without him. Professor of physics at mathematics at Columbia University, Brian Greene. Or as I like to say, the Pete Townsend of physics. Anyway, thanks to all of you for being here. We begin with a moment of physics from Brian. Our second data point is that spectacular Beethoven. It seems to me the question that I want answered right at the top is, we can go way back before physicists and mathematicians in terms of thinking about multidimensionality. Linda, describe some of that history if you could.
Okay. We might get the first a slide up that'll give you a little bit of background. When Kaluza began thinking about an extra dimension of space, he was not doing it in a vacuum. In fact, from the middle of the 19th century onward, there had been quite a good bit of interest in mathematics just by formula that went up an extra dimension. And it's really in the 1870s, 1880s that this comes to popular attention. And I'll show you a couple images from a wonderful book from 1913 produced by a Rochester, New York architect named Claude Bragdon called The Primer of Higher Space, happily, which is available as a PDF online. It's been digitized. And it's the most wonderful compendium of the way, in the year 1913, one might think about a fourth dimension of space. He's focusing on a fourth.
And Claude's motivation here was what? He wasn't necessarily trying to describe the universe. He was trying to get beyond just sort of point, line, plane.
Exactly. And the idea that between, say, the 1880s and Flatland, Edwin Abbott's book that's published that year, that really is the first major popularization of this idea, and about 1920, when Einstein's theories really are popularized. This idea is incredibly popular. So in 1909, Scientific American has an essay contest, What is the Fourth Dimension, in 2,500 words, published those essays, and it's just a remarkable draw, I think, so stimulating to the imagination that indeed the world might have an extra dimension, and Flatland was the great cautionary tale. How could we deny this just because we could not see it? Are we as narrow-minded as those Flatlanders in their plane, not realizing they're embedded in three-dimensional space? So just typically, you can see geometrically one goes up, as John was saying, from point to line to plane to cube to hypercube. And you've seen such beautiful computer graphics already this evening, and it's just a measure of how in the 1980s, with the development of computer graphics, this capability of visualization has just been transformed, because we're going back to someone who's working with a pen and paper, trying indeed to suggest this complexity of space. And
so in a sense, you're saying the great graphics that we have today on all of these sort of computers and devices that we use are a restatement of this original impulse to visually try to get beyond three dimensions. And so even though they may be creating special effects for scientists to use at conferences, they're also artistically very much in this tradition.
Absolutely, and there are certainly artists working today who are drawing very much on this power of the computer to aid as an aid in visualization. But if you were in 1913, these would be your representations of the fourth dimension, typically. The hypercube here at the bottom seen as an isometric projection and as a perspective projection. And then the hypercube seen as folded down into three spaces. If you were cutting a box, a cube, laying it down in two space, or this cruciform hypercube that comes to be a symbol. And it's really just a symbol, because clearly it's not the way this would look in four dimensions. So this attempt to visualize this invisible dimension relies a lot on the analogy of 2 to 3 dimensions, thinking about those relationships to go from 3 to 4. And there's another slide here that will show us another way that people often attempted to grasp this idea was to use time not as the fourth dimension itself. That's really an Einsteinian idea, Minkowski. This is time as a means to think about a higher dimension, the way that we might imagine a sphere, as in the case of Flatland, passing into the plane of the Flatlanders, or this wonderful illustration of Bragdon with these cubes passing through at different angles, which to the Flatlanders appear to be all different things when in fact it's a single object. And I think
so we have animations of those. Let's
do a video of that.
Great.
Yeah, let's roll the sphere animation first, and then the cube animation, and then we can talk about the implications of that.
So maybe just breaking what's happening here is a sphere is passing through a plane. So if we were two-dimensional beings living on the surface of this plane, unable to see anything off this plane, what would we see? What we see as the sphere comes in. So from this perspective right here, if we're a little flat being on this two-dimensional world, as the three-dimensional sphere passes through, we just see this growing shape. It's actually a circle that gets bigger and bigger, smaller and smaller, and we would actually just see what looked like a line getting bigger and smaller.
With strange little endpoints on it.
That's right. That's right.
And we would have endless conversations about why is it getting bigger? Why is it getting smaller? What's it doing?
So like right here, we don't see anything at all. All of a sudden,
here's a cube.
Pops into our world. It's growing larger, larger. We're like, what's going on? There's this big thing. It's getting bigger.
It's a triangle, but then it becomes a square, and then it goes back to a triangle.
Exactly.
And physicists would argue, flatline physicists would argue about this forever and ever until somebody came up with a brilliant idea. It's not a triangle becoming a square, you idiot. It's a cube going through the space.
That's right.
And that's sort of the shifts, the perceptual shifts that create this whole dimensionality.
You got it.
That's brilliant. So, Brian, who preceded Kaluza? Who preceded? Yeah, I don't get any credit for this. You know? He could just say that friendly. Who preceded Kaluza in the scientific realm?
Yeah. I mean, as Linda was saying, there's a big prehistory to Kaluza that really comes out of the mathematical tradition. You know, mathematicians in the 1800s, people like Gauss and Riemann and others, were trying to develop the mathematical tools for describing curved spaces. Because little by little, people were recognizing that the geometry that we got from Euclid, which was the geometry that we learned, in high school about objects that live right on the surface, on a plane, that was one kind of geometry, but not the only kind of geometry. There could be shapes that live on arbitrarily curved surfaces. Now, the thing about mathematicians is, when they come up with a new idea for describing some sort of new entity like curved space, they recognize that they can be quite general about it. It doesn't have to be 3 dimensions or 4 dimensions or 5 dimensions. I mean, when you talk about 3 dimensions in school, you talk about X, Y, and Z.
Right.
It's the same thing. When you're going to a dinner party, you give a street, a cross street, and a floor in order that you know where you are going. 3 pieces of information in 3 dimensions.
Unless you're in Iowa, which is the flatland.
That's exactly right. Now, if you think about that for a moment, it's not so hard to go from XYZ to XYZW or XYZWPQR. It's just additional letters.
Mathematically, there's nothing additional one needs to know to create these multi-dimensions,
right.
even though it's a huge leap for us in the physical.
That's right. So mathematically, it's very easy to go to n dimensions, arbitrary dimensions, and these are the kinds of mathematical tools that were developed in the 1800s. Einstein borrows those tools in developing the math behind general relativity. In the video I showed, space was nice and flat, and then it curves. He used the mathematics of curved spaces to describe mathematically what was going on. Kaluza comes along and says, but wait, that math is easy to talk about in any number of dimensions, and he goes up by 1 and starts to run from there.
Mm-hmm. So, Lawrence, how much of this constitutes a sort of need to get beyond the senses versus a looking at this tension of, well, math says this works perfectly well, even if I can't see it?
Well, I mean, that's really interesting. There's a huge difference between mathematics and physics, which some of us understand, the mathematicians are free to imagine any possible world, and physicists are constrained. Feynman said that science is imagination in a straitjacket, and so, which is true. I mean, we're forced, unfortunately. There are things we think are beautiful, and we all work on them, and many times they're wrong, but the universe tells us the way it is. And so when we're imagining the possibilities, we borrow from the mathematicians because they provide us the tools, and when we try and see if those tools will describe reality. And if you're a theoretical physicist, it's intimidating almost when you're sitting working to think that when you come up with something that it actually might be real. But what you have to be skeptical about is something beautiful to you because we're hardwired to like beautiful things, or because it relates to reality. And I think with extra dimensions, as an example, people are hardwired to want there to be more out there than meets the eye. I mean, it's the story of human history, the idea from religion on to want there to be a better world, a more beautiful world, or a darker world sometimes. And so if you look at physicists and artists and mathematicians, there's been a long history of looking at extra dimensions, the idea that there could literally be whole worlds we can't see. And what we still don't know the answer to is that fascination due to the fact that they actually exist, or just due to the fact that we're hardwired to want them to exist?
Shamit, I want to get into some of the concrete, sort of off the deep end elements of this extra dimensionality as it relates to superstring theory, et cetera. But first, let me just, taking straight off what Lawrence said, how much of the artist's history of this is about trying to describe something that's real versus simply, hey, what if we could do this kind of thing? Just a pure flight of fancy.
I think it's very central to a lot of early 20th century art, and this fascination with the fourth dimension, this widespread popular literature, was augmented by the discovery of the X-ray in 1895. So there's an image here, I think, of a Cubist painting here. We can, certainly for much of the 20th century, in the wake of Einstein, we've thought of the fourth dimension as time. And we need to go back before that point to the era of Cubism, before World War I, and put this spatial fourth dimension back into play to really help us understand that a painting like this portrait isn't just Picasso being difficult for the sake of being difficult. Yeah. He considered himself a realist. But in fact, in this period, just in the wake of the X-ray especially, this realization that the human retina was picking up just one range of vibrations in a much larger electromagnetic spectrum, that there was a reality out there invisible to the human eye, is tremendously liberating for artists, and that Cubism in so many ways is a product of this moment and interest in X-rays, in radioactivity, matter dematerializing into the space around it. And one got very often these kinds of comparison photographs of the external rat, the sense that indeed artists through history for centuries had focused on that fur, on capturing invisible light in visible light, the external appearance of something, when in fact there was a reality, an interior reality. And that, I think, had a tremendous effect on continuing interest in the fourth dimension, because that idea might have remained for quite a time the realm of philosophers and mystics and others. But in fact, in the wake of the X-ray, who could say there wasn't a fourth dimension just because you couldn't see it?
And John, maybe it's worth saying, if there were a fourth dimension, you could actually see inside the rat, just like that. You wouldn't need X-rays. You could actually just see right in.
In fact,
I mean, just to give it, just so it's clear, like in Flatland, if you had a living being in a flat world that, say, had an external circle as its epidermis, as its skin, and it had organs inside, in the two-dimensional world, if you were there, you'd only see the skin. But when you go to the third dimension, you can see right inside and see the lungs and the heart and whatever internal structure there is, just like we're seeing there.
And that sounds like a really good thing, and I'll let you go in a second. But in fact, we know that X-ray is in fact a different frequency of electromagnetic radiation that refines an image in a different way and gets beyond the surface of the skin. So while Picasso might suggest that the interior of the rat vis-a-vis the point of view of the X-ray is a different dimension, it's more of a commentary on our senses, in the sense that we see this. That's an arbitrary fact of nature, but if we had an X-ray machine, we could see this. This painting is an attempt to say we might see all of it together, but that's short of new dimensions, right?
No, they were really influenced, as I learned from Linda, they were really influenced by in fact, the interest in a fourth dimension. They got it wrong because the fourth dimension was time, but they became fascinated by the idea of fourth dimension. You can go on because you'll do it better than me.
Let's just go to the next slide, which is just to suggest that there is a very real awareness of these this remarkable man, Jouffret, who was doing remarkable new kinds of illustrations of complex four-dimensional solids. And we could say that in Cubism, there generally is a recognition that reality is more complex than what the eye sees. Matter transparent, dematerializing, but also there's a geometric substructure in this painting that suggests very much that in the wake of his own interest in Cézanne and a geometry in nature, there's a new kind of geometry here that suggests a inner structure and a geometrical structure. So it's a painting, I mean, this is, again, you're limited to canvas and oil paint, and it's a painting that at least keeps us from saying that space is three-dimensional. We can't say that. And I think in the end, that's probably the way in which the Cubists are most successful, is in a negative sense of denying our traditional way of reading.
Denying and also sort of manipulating the senses to suggest other possibilities. You must, of course, depart from the senses entirely to explore string theory and the sort of cosmological questions that you deal with. I mean, how useful is extra dimensionality as a tool for describing reality as opposed to simply, hey, could it be this way?
Well, let me try to respond to this sort of, hey, it would be cool if there were extra dimensions kind of thought that may have occurred to many of you as a motivation for string theorists. So physicists are naturally actually very conservative people. And we will only depart from what's been tested in experiment if there's a really compelling reason. So Brian touched on this in his opening presentation, but if we could we get a picture of a graviton on the screen? I think we have a picture of a graviton.
Now, this is like proprietary, never before seen, except on this stage, an actual graviton?
Right. Okay, so So since we haven't yet seen a graviton, we're free to imagine it however we wish. I guess this is how the artists wish to imagine it. Now, my point about this graviton is this is the quantum particle that is supposed to transmit the force of gravity as Einstein described it in general relativity. So as Brian explained, general relativity says that gravitation is merely the actual bending and twisting of space-time geometry caused by a massive body. In quantum mechanics, that means there must be a particle that the massive body emits that goes and tells space-time how to bend. It's called the graviton, and while we haven't observed it yet directly, we're all pretty damn sure it exists. Now the nice thing about this is, although we're sure it exists, and we have a beautiful theory due to Einstein of the classical theory of gravity, we do not have a beautiful quantum theory of gravity, a theory that can take that graviton, smash it together with other gravitons at very high energy, and produce answers that make any sense at all. The theory is mathematically inconsistent. And the way that extra dimensions reappeared in the mid-'80s was not out of some fanciful thoughts of drug-addled physicists, but it was because a new theoretical structure, superstring theory, was shown to produce a quantum mechanically consistent theory of the interactions of this graviton. Now, let me get back to your real question. Can we have the picture of the fifth dimension of Kaluza and Klein again? So Kaluza and Klein originally came up with a theory where the reason that electromagnetism exists would be similar to the reason that gravity exists. It was that secretly space was 5-dimensional. So if you imagine M there, it's drawn as a line here, but you should imagine that's all 3 space dimensions, is our space. What Kaluza and Klein realized was by adding a little extra circle, so small we couldn't see it, Einstein's same mechanism of explaining gravity as fluctuations of the geometry of M would now also create electromagnetism if one allowed the extra dimension to fluctuate. Now in string theory...
So what exactly is fluctuating there? Something going on inside the tube?
Yeah, so let me speak very roughly. You see there's a circle above each point in M. It's like the circles in Brian's earlier drawing.
Right.
And very roughly speaking, what's happening is the structure of that circle is fluctuating. As you move over the different points in M, it can have slightly different size.
So gravity interacts on M, electromagnetism interacts within M by C.
Yeah, or roughly, actually, the whole theory is just gravity in all 5 dimensions, 4 plus 4 of space and 1 of time. It's just gravity, but to a poor ant confined to M, it looks like gravity plus another force.
We're the ant.
We're the ant.
We're the ant.
Right.
Okay. Not you. Me. Yeah, there we go. Okay, so this extra dimensionality is a question of scaling and point of view. Now, it sounds a little bit convenient that the physicists say, we're supposed to not be able to see it.
Well, I just want to, I keep trying to figure out why I'm here, and I think,
You wrote a whole book on this.
Yeah, I know, I did. That's right. But no, this is indeed a fascinating argument for extra dimensions, but in fact, the first place they arose in string theory was not in the context of gravity. It was, and so was in the context of trying to understand one of the other forces of nature, the strong force, which was also inexplicable at the time. And strings were invented to try and resolve a big problem in there. In that case, it needed 26 dimensions. And so I want to point out that there have been physics reasons to be interested in extra dimensions, and those turn out to be wrong. Now, this is a very good reason to be interested in extra dimensions, but it could be just as wrong, and I just want to sort of temper that.
So I mean, I would absolutely agree with that, and I think it's really important to underscore that everything that we're talking about tonight could be utter nonsense. Yeah. However, there's strong motivation to think about these ideas because, as Shamit was saying, we have a theory of gravity, Einstein's general theory of relativity. We have quantum mechanics. These two theories, each of which works fantastically well in the domain for which it was developed. Quantum theory for small things, general relativity for big things. Now, we think the universe is overall consistent, but these two theories don't work together. As Shamit was saying, they're internally inconsistent. The wonderful thing about string theory is that it's able to put them together in a consistent package. One package, gravity, quantum mechanics, it's all there, but the math only works if you have extra dimensions. And that motivates us to take it seriously. It doesn't mean we know it's right, by any means, but it motivates us to take it seriously and analyze where it takes us.
Yeah, we agree on that.
Do experimental physicists accept this hey, the math works, just stop questioning it, just go find an experiment that's going to prove it? Or is it like the way it used to be in the 1800s, where you really needed to design an experiment to show physical evidence of this phenomenon, and then you worry about the math later?
No good experimentalist listens to theorists ever. So they're duly skeptical. They understand the motivations. Unfortunately, we do not yet have evidence for extra dimensions, but in all the forthcoming generations of experiments on cosmology and on particle physics, people are hunting for hints. And those hints are not an inevitable consequence, even if string theory is correct, but they would be our first window into it if they are.
We don't even know, I think it's fair to say we don't yet even know what all the hints are. It's not as if yet, I think it's fair to say that we understand completely the mathematics, so we know what, in all cases, unambiguous predictions to make. We're still struggling with the mathematics. Absolutely. And so it's even one step further.
Let me step back for a second. I mean, Kaluza was going for dimension number 5, right? Now, are we absolutely certain, because the artists don't seem to be, that dimension number 4 is time, Lawrence?
Well, we are certain of that. And in fact, the picture, it's kind of interesting. The picture we have with time being a fourth dimension is not that different in a sense than the picture Brian showed of the cube going through a plane, because really what we're learning is that that when we separate space-time into space and time, we're seeing different projections of a four-dimensional universe where time is an extra dimension. And so that we're seeing different three-dimensional slices, and different people with different perspectives would see one person's space be another person's time. Now, with 4 dimensions of space, the different perspective comes from rotation. But it turns out, in the way the world works, the way time is connected in space, that different people have different perspectives if they're moving at different speeds. And so you can find out that, in fact, that one person's space will be another person's time. And that's the basis of special relativity, that what we're seeing when we call the length of a rod the length of a rod, and a person moving fast compared to us will see the rod as being smaller, well, they'll see him smaller in space, but the different ends of the rod will be stretched out in time. And so one person's space can become another person's time. So the content of special relativity was really to tie together space and time in a different way than rotations do in a nice four-dimensional space, but it works. And it's not just hypothetical. We measure it every single day, right, in particle accelerators around the world, that when you're traveling very fast, your clocks slow down. All of those implications come from that relationship.
And those fabulous thought experiments that when you're introduced to relativity in high school and college, as hard as it is to make the leap, is really a restatement of the idea that in these multiple dimensions, the various dimensions can be pulled and moved, and time is just another one, and the way that happens is the way Einstein describes it.
You know, and I wanted to even go back further, way further back than what people talked about. To me, the real person who first kind of talked about this was really Plato. When Plato was a natural philosopher in principle, but you probably got forced in school to read the Republic, maybe some of you, or maybe the non-Americans. And
whoa!
But anyway, he gave that analogy. Perhaps. He said, well, what we're seeing is a projection. He argued that it was like people sitting in a cave their whole life, just looking at the wall of the cave. And looking at the shadows of reality, they had to determine the reality on their side. And sort of, in some sense, you can think of the two-dimensional shadows trying to infer the three-dimensional world. And in fact, what he said is, if you really sent a mathematician out to look at the world and came back and tried to explain what was really going on, everyone would think they were crazy. But his analogy that we have to, the job in his mind of a mathematician or a natural philosopher was to infer the underlying reality, which in this case really was an example of an extra dimension that you had to infer from looking just at the shadows. And the shadows are a very good example, I think, of the kind of thing that you see when you see rods shrink. If you took the shadow of my hand on that wall there, and it has a certain length, and if you only knew of 2 dimensions, you'd see that length. But if I rotate my hand, the shadow's going to look smaller. And if I looked in that world, I'd say, gee whiz, something's happening. Length isn't invariant.
Or you would just call them 2 different objects. You would say they're 2 different
exactly,
objects.
You'd think it was different. But if you know about the extra dimension, you see a connection. And that was a sort of connection that Einstein made. And in principle, it's the connection that we're trying to make with extra dimensions in string theory or other ideas is that somehow we're connecting things that seem very different by allowing this extra dimension. And it's a beautiful idea, and we just don't know if it's right, but it's a beautiful mathematical idea.
Just take that one more footnote on that. The things that we believe we're connecting by going up to higher dimensions, we believe that all the forces of nature, not just electromagnetism and gravity, which is what Kaluza was focusing upon, but we know that there are other forces of nature. Now, the strong nuclear force that's vital for keeping atoms together, the weak nuclear force responsible for things like radioactive decay. We believe in the context of string theory that gravity, electromagnetism, the strong nuclear force, the weak nuclear force, all of those are united by going to this more unified perspective of a higher dimensional setting. So it's a very beautiful picture. Doesn't mean it's right, but it's a very beautiful picture.
Go ahead, Sean.
Let me pick up on that a little bit. Could we get the picture of the standard model up there? So the shadows that we see that we're trying to interpret as evidence for new physics, be it string theory or some other theory we haven't come up with yet, are these shadows. They're the shadows that your fine taxpayer dollars pay for us to discover at Fermilab and at CERN. Well, I guess that's European tax dollars.
Some of our tax dollars are there, too.
Some of our tax dollars do. Okay, so you see here, this is the table of, this is the modern day periodic table of elements. Instead of, different kinds of atoms, you see here the different electrons and quarks, and they all have cousins. So you know about the electron, you probably know about the proton, you're made of protons. But for each elementary particle we know, it turns out there are cousins you know much less about because they have no apparent reason to be there. They don't play a role in chemistry, they don't form parts of your body. They're copies of the electron that are more massive that we've found, copies of the quarks that make up the proton that are more massive that we found. This is a shadow. There's a reason that there's such structure. Why are these things repeated many times when there's no apparent need for day-to-day physics? Now, in the periodic table of elements, seeing that repeated structure eventually led people to understand that atoms are complicated composite objects. And the hope here is that this particular shadow, this complicated pattern of many different forces and many different particles, is a hint that there's a single underlying object, perhaps a string, whose different windings or oscillations can really unify this picture. Say it's not just some, God had a bad day and decided to use 15 particles instead of 12, but that really she or he used one, and these are its different manifestations.
John, do you mind if we do a little video that amplifies this? But
let me just ask one dumb question, okay?
Yeah.
Just one?
Just one, okay. Yeah, I know. It's going to be a long night. One can use multidimensionality to describe this complicated and frustrating sometimes model, but there's also this idea that in the sort of Higgs substrate, the sort of Higgs domain where all these things are unified, it's at a higher energy level, or it's at a higher level of sort of other phenomena going on, and that when we see these other particles, it's because the energy level, as is the case in the Big Bang, goes down and they sort of pop out in the way that ice sort of emerges at a lower temperature than water, that sort of thing. That doesn't imply multidimensionality for these things to exist and to be fleeting, right?
Absolutely not.
So
that's why string theory is one of many possible ways of interpreting this kind of shadow, and I think the shadow of the graviton, which is a little deeper and harder to interpret.
And in fact, to be fair, I mean, the string theory is sort of followed on an idea called grand unification, which is really motivated actually by experiment, that the three of the forces of nature, taking gravity aside, three of the forces of nature, the strong, weak, and electromagnetic force, their strength varies with length scale. And if you extrapolate for what we see now, and you go to a very small length scale, about 15 orders of magnitude smaller than what we can measure, maybe 14 orders of magnitude smaller than what we can measure with present-day accelerators, you'll find that the strength of all those forces, which is very different on the scale we can measure now, looks the same. And that's very suggestive to people that maybe those theories do get unified and really represent different manifestations of a single force. And in some of those same theories, these families can result, these different shadows can result from a larger underlying symmetry group. And in that case, it doesn't result from extra dimensions. The
idea there being that it would make more sense for these forces, these particles, these shadows to have more space to work in their little domain, their little dimension, that there ought to be dimensions for these shadows that we never see to have length, to have duration, to sort of have a bigger life.
Actually, can we get a picture of a Calabi manifold up here?
Well, actually, Shaman, if we go, there's a direct video that we have that I think will illustrate this. So everyone is right. String theory, again, is just one possible way of explaining how this goes. But let's look at what string theory actually says in terms of trying to explain this stuff. So if you bring up the horn, the French horn video, the idea is if you have a French horn, the vibrational patterns of air is dictated by the shape of the instrument, of course. Similarly, if you replace the horn by one of these extra-dimensional spaces, a Calabi shape, if you imagine strings vibrating, strings are so small that they don't just vibrate in the 3 dimensions that we know about, they also vibrate into the extra dimensions. They live partly in the extra dimensions. So just like the shape of the instrument affects how air vibrates, the shape of the extra dimensions affects how strings vibrate. So when strings vibrate in one pattern or another, they will look like an electron, or they'll look like a quark, or they'll look like a muon, or they'll look like a photon. So the extra dimensional shape dictates the possible vibrational patterns, the possible notes, if you will, that the strings can play. And if the possible set of notes that strings can play, the possible vibrations, agrees with the collection of particles that we've seen in the world around us, that would be showing the shadow. The particle properties that we see would be the shadows. The true underlying physics would be strings vibrating in these extra dimensions. And the wonderful thing is that Shaman showed that there are 3 families. You got electrons, muons, and taus. You got the up quark, you've got the top quark, you got the strange quark. So they all seem to occur in these 3 patterns. In string theory, that number 3 might reflect that strings, if the extra dimensional shape had something called an Euler number, the number of holes that it has. So just to use general language, if the number of holes that the extra dimensions has, if that number is 3, if it has 3 holes, then there would be those 3 families. There'd be 3 shadows. So that is a possible explanation for what we see coming from this more unified setting of extra dimensions.
So describing this sort of interactivity, if you're going back to the French horn model, by simply looking at what's coming out of the bell,
yes,
you're going to get one small picture, but you have to understand that there is music and interaction that is directly corresponding to the piece that you're hearing in the concert hall, taking place at every point in the French horn itself.
Yes, that's right.
But I want to amplify what you said earlier, because I don't think maybe it wasn't clear enough, that is actually a very real possibility. But there is also the possibility that all of this structure could come in 3 dimensions of space from a unified theory of fields at a scale much lower than where gravity
within 3 dimensions.
And there are simple, beautiful, some people would think beautiful mathematical representations that give all of the families. So there's different mathematical pictures, and we just don't know. We have no idea right now, which is why we want to do experiments.
Linda, when the physicists came and said that the 4th dimension was time, I mean, were all the artists annoyed, and did they then immediately abandon their trying to create this 4th visual dimension?
Well, I think it must have been a great shock, because a good many artists were really invested in this notion of higher dimensional space, and it's remarkable because it does hold on through the 1920s. It's really a gradual decline, but if one thinks of the whole century, it's certainly the century begins with the spatial 4th dimension as the dominant mode, and then, say, for the later 1920s through probably the 1960s, time as the 4th dimension really dominates.
Wouldn't you say, I mean, I learned a lot of what I know about this from your books, but that actually it was the opposite. The artists, I think, were inspired. I was at a dance thing in the World Science Festival, and we were talking about that too. I think people get inspired by physics even if they get it wrong. And so, no, and there's nothing wrong with that. I mean, science should be, part of the beauty of this festival is that science should inspire culture. It doesn't have to inspire, it can inspire poetry. It doesn't have to be an exact physical representation. And in fact, the artists in Paris, the Cubist artists, were influenced by Poincaré. I mean, and the physicists were saying it was time. The artists loved the idea so much and made it space, and it didn't,
But the physicists weren't really saying it was time yet, and certainly no.
1905, I think.
Well,
by 1908, certainly.
It's not publicly known. That's the thing. It's definitely not publicly known in France, where Poincaré is the giant, and there's a real resistance. I mean, there have been wonderful studies about the reception of relativity, and there is a good bit of resistance. So it's really not until the eclipse In 1919, and the announcement of the Eclipse expedition, that Einstein becomes a celebrity.
Sure.
That's
That Einstein-
the-
All right, but let's explain the experiment.
Okay.
What happened? All right, the eclipse allowed, and I'll give this one to you, Linda.
Okay, I'll take
the
it.
eclipse allowed us to test what aspect of relativity?
Okay, so one of the postulates of Einstein's general theory that light would be bent by the mass of the sun, and this was Eddington's expedition at the time of this eclipse, which established the correctness of that postulate.
Blocked out enough of the sun's light that you would be able to actually measure the bending of light.
Exactly. And that really makes a difference. So while Einstein is certainly known in the scientific community, he's not known to the public until that point. So, but it's true, artists were then greatly inspired by Einstein and by the idea of time as the fourth dimension to introduce time and motion into works of art and make kinetic art. And there's a whole other range of artistic response that occurs to Einstein's theories, but it really is something that doesn't happen until the late teens or early 20s, basically. And then I think this becomes, if one could hitch one's wagon to Einstein and prove that your art somehow, for the middle of the century, that's a guarantee of your avant-garde status. And space-time are the magical words, and if you can somehow connect yourself to that, that's...
Well, that hasn't changed. We all now get manuscripts from 1,000 people around the world. They're trying to depose Einstein with all sorts of crazy theories, because again, if they can do away with Einstein, they will then rise.
No, but is the analog working with string theory? In other words, are there artists coming to you and saying, I've got a really great idea for sculpture?
No, artists come to me, and I suspect other string theorists all the time, who love the ideas and want to, as Lawrence is saying, not really represent it literally, but they just find it so exciting, these ideas of vibrating strings, extra dimensions, these possibilities, and they want their art to somehow reflect it. So, the dance piece that Lawrence was referring to today was by Carol Armitage, and honestly, she read my book, The Elegant Universe, and said, I want to do a dance piece. And I was like, really? What would that be? And then she creates this thing. And if I looked at it, would I know it's string theory? No. Would I know that it really came from my book if I didn't know? No. But nevertheless, there are interesting ways in which she's processed those ideas from the lens of a choreographer, and it's very interesting.
And actually, to be fair, I think one of the reasons that string theory is so, besides, of course, Brian's excellent books, that string theory is so popular among the public is it's so graphical. People love the pictures, and it's really easy to see, and it inspires them, this idea of strings, and that's great, but that doesn't mean it's right.
Opiate of the masses bit?
Was that?
A string theory, opiate of the masses here in the 21st century?
You said it, I didn't.
Yeah. So, I want to sort of conclude our discussion with some sort of look at concrete attempts to detect some of these extra dimensions. But before we get there, a lot of the story of the 20th century and the excitement over physics and describing reality that, was in some sense derailed by some of the more sober phenomena that happened in the 20th century, World War I, World War II, the development of the bomb, and culture, I think, became rightly afraid of some of these concepts because of the way history transpired in the 20th century. In the 21st century, here we are at the beginning, there are a lot of the same sorts of turmoil and an attempt to understand the theories going on as well. In the 20th century, it took a long time for people to internalize relativity, and I think we're still having that problem. Where do you think string theory and some of these ideas of extra dimensionality are going to appear either in popular culture or in art that you're observing now, Linda?
It has been so interesting to watch this. As someone who wrote on this topic in the 70s, I was saying to Brian when I continually had to tell people I was not talking about time as the fourth dimension. It was this other idea. And to have the combination of string theory and computer graphics emerging in the 80s, so graduate students' dream to have one's topic suddenly become so relevant and universally interesting. So I think certainly even before that change, in the late 50s and 60s, Martin Gardner in Scientific American was starting to write columns about the spatial fourth dimension, had gotten interested in this idea again, and one sees this gradual emergence, which for artists, say in the 70s, by that point, space-time and kinetic art seemed to be used up in some way, and there was this suddenly seemed so iconoclastic to discover again this spatial fourth dimension, and then to have this remarkable cultural revolution. So that I've been tracking Google sightings. So, for example, there are matches in say 2002 or so. When I think if you searched fourth dimension plus space, I think I got 17,600 matches. And doing it this month, there are 2,800,000 and something thousand matches. And part of that is the books on the topic. Part of it is the 2 Scandinavian heavy metal bands that have albums called Fourth Dimension. You can tell it's really spread.
Right.
But nonetheless, it is a remarkable renewal of...
And just consider how lucky the scientists were in the early part of the 20th century not having to worry about Scandinavian heavy metal bands creating all that noise. Lawrence, go ahead.
But again, it's interesting that there's this sort of, it has been cyclical in the century. And when you point out that Scientific American, it wasn't described the possibilities of a fourth dimension. It was this essay competition, 1909, described what the four-dimensional is like. It was like, we know it exists. Describe it. It's amazing if you look at that science. So there have been periods of time and this could just be another, another fad. I'm talking about the Scandinavian rock group, but not.
Well, no, Scandinavian heavy metal, that'll be around for a while. I mean, that's long-standing.
You're right.
Doesn't require experimental predictions. Shamit, you get the sense with the Large Hadron Collider and some of the experimental work that's being done, and it's not even clear if LHC is going to have anything to do with the string theory or these extra dimensions, that the science is more remote than maybe it was in the era of the Cubists. As revolutionary as those ideas are, that for us to reach and try to make the dance piece about Brian's book, or to create the sort of art that causes a similar kind of conceptual flutter in regular people who maybe aren't scientists. Do you see evidence? Do you see places where we'll have discoveries that actually people can understand outside of pure mathematics?
Sure. Well, let me describe in a minute one way where even in the next 5 years we could get direct evidence of the existence of extra dimensions. But before I do that, and I know string theorists are always doing this, I want to sort of make a plea for people to remember how long a time it takes in science, even given the correct idea, to produce the smoking gun. And now a favorite example I have in the era of the LHC is the previous big Nobel Prize discovery in particle physics, the discovery of the force-carrying particles of the weak nuclear interaction. Okay, the famous theory, the first famous really good theory of these interactions was invented by Fermi in the 1930s. It was based on physics that, relative to what we're talking about now, was pretty well understood. There was a lot of evidence it was correct, even experimentally. It took 50 years from the time that Fermi wrote down his first correct theory for these particles to be produced. Okay? Now, in string theory, the leap that we're making in terms of scales in energy or scales in size to the size of a graviton, okay, is so much larger. One should not be surprised if, like many things in science, it takes a long time to play out, and we'll see what's right and what's wrong. But let me give you a very optimistic way that things could play out, okay? And I think very few people would advocate that this is the way they will play out. But could we get the picture of the fifth dimension and Kaluza and Klein back, the Kaluza-Klein theory back up there again?
It's the one with the line and the tube.
The line and the
right?
tube.
The
Absolutely.
little line and tube
So
thing,
what's different about the top picture from the bottom? It's that there's a circle on top of the line. Okay, so now we have the LHC. In this cartoon, what is the LHC? You have
the Large Hadron Collider there at CERN. Okay.
Large Hadron Collider. You take two particles in M, you smash them together with really high energy, you look at what comes out. Okay? And if you're really lucky, you discover new particles that way. Now, if that picture were literally correct, and if the radius of that circle, if the size of that circle were just at the right place that the Large Hadron Collider can probe physics of that size, which is a big assumption that many of us are skeptical about, then one of the things that you would produce is five-dimensional particles that could go around the circle. They would have momentum in the direction that we can't see, the fifth direction. Now, because we can't see it, we wouldn't see that as a velocity in our space. It wouldn't look like a moving particle. It would look like a more massive cousin of one of the particles that we already know about, one that has 1 unit of velocity in the fifth dimension, or 2, or 3. And that repetitive structure, that you'd get a tower of particles, very similar to what we've seen before, but there can be 1 or 2 or 3 or 4 extra units of mass that's related to basically invisible velocity in a fifth dimension. That's called a Kaluza-Klein spectrum, after Kaluza and Klein. And if the LHC is at just the right energy to detect that dimension, we would see that as a smoking gun of extra dimensions.
But you would detect it as a small thing and see its behavior as something much more massive.
Absolutely. You could be very stubborn, and you could say, even if you saw 7 such particles, the electron and one with 1 unit of momentum and 2 and 3 and 4 and 5 and 6, you could say, what are you talking about extra dimensions? We have here 7 electron-like particles with this regularly spaced mass. You can say whatever you want, okay? But the fact is, Occam's razor in that situation would tell you the most useful way to talk about this situation is that we have discovered a 5th dimension. Now, again, that's an example of where in an experiment you could see signs of this. I'm not advocating that we will see signs of it, and my own research and that of most string theorists, even those who believe firmly in the existence of extra dimensions, probably suggest that we won't see that. Okay? But it's an example of how these ideas really do become testable. It just takes time.
I certainly agree that that's, and I think all of us on the stage would agree it's possible. All of us, the physicists on the stage, would probably say we don't think it's going to happen.
Absolutely.
But it certainly is a possibility. But I feel obliged to temper what you said. The Fermi's theory, he won a Nobel Prize because actually he explained things we measure. And then within that time, there was a neutrino discovered, which is a key part of the theory. I mean, there were a whole slew of experimental discoveries in those 50 years that really played a key role in our understanding. And so it is a little bit different. And we have to realize it's been a challenge, and it's been hard times. And the string theorists, and I know Brian and I agree completely on this, that right, Brian? That it has been somewhat frustrating. That I think expectations in the 1980s, I think, were much higher than they are now. And it has been a difficult time as people have learned the theory is more complicated than they imagined. The predictions are more difficult than they imagined. And it's been a long, fallow time, I think. And that may not mean anything. It's just been difficult.
On the Fermi scale, we still got 20 years to go, though. I mean, right? Can we just back up 1 second? Can you explain how the Fermi problem is much more accessible than the string problem? When you say Fermi described the weak interaction.
Absolutely. Let's talk about
quickly.
Sorry?
Yeah.
I said, let's talk about microscopes. Okay, so I actually don't know anything about microscopes or how they work, but you could imagine if you look at the history of the microscope, at a certain point you were able to amplify, your hand with a fancy microscope well enough to see, a little patch of skin, and as time goes by, you see littler and littler patches. If you got a really powerful electron microscope, maybe a scanning tunnel on electron microscope, you start to see the atoms in your hand. So a useful way to talk about the advance in technology there is, over what range of distances did your resolution improve? If you went from a patch this size to a patch half that size, it's a factor of 2. If you go from a patch this size to being able to see the atoms with an electron microscope, that's a factor of 10 to some large number, 10 to the 10, something really big. Now, in Fermi's day, physics was done at a scale of a certain distance scale of the size of a nucleus, maybe 10 to the minus 13 centimeters, the size of an atomic nucleus. And to go to the energy where you could directly produce the particles he was talking about, really put the stamp on his theory for sure, understand exactly how it worked, that's a factor of 100 over the scale that Fermi was already familiar with. When we talk about string theory, and not the extreme versions where there's a very large 5th dimension or something like that, but what most of us think string theory is, or when we talk about Einstein's theory of gravity and say, where should quantum mechanics become relevant in its interplay with gravity,
right.
The ratio of scales we're talking about between the Large Hadron Collider, which is by far the biggest and best machine we have today, and that typical size scale is 10 to the 15. So Fermi's factor
Beyond
of 100.
Bigger number than 100.
Much bigger than 100. Right. So we need an awful lot of money, and you're welcome to fund your own accelerator.
All right, but understanding the scale, I think, is really important. Brian, go ahead.
Well, I mean, just to amplify 2 points. One, just to get a sense of the kinds of scales we're talking about. In the traditional way of thinking about string theory, if you were to take a single atom and magnify it to be as large as the observable universe, it's a huge scale of magnification, then the traditional way of thinking about string theory, under that same huge scale of magnification, a string would grow to be roughly the size of an average tree. So one way of thinking about it is, a tree is to the entire universe as a string is to an atom. That's how much smaller we're talking about, possibly, and that's why, as you say, it's so hard to test these ideas. And you're absolutely right. Back in the 1980s, when I was a graduate student and these ideas first came around, I'd work until 2 in the morning in my office. I'd bike home. I'd get up at 7, I'd be there so that when the mail came in, I could get the preprints that people had written around them because I just wanted to know. It was so exciting. And people were saying this could be it, this could be the final theory. And as a young graduate student, it fired you up like nothing else. And it was premature.
And now you go to the mail and it's like, could I do a dance on your book?
Yeah,
oh my
exactly.
God.
Exactly
I mean,
right.
where are we here?
Let me. Oh,
Go ahead, Lawrence, and then Sean. Okay.
Well, I want to put this in perspective. I think Brian captured it. And the point is, we make fun on different sides, but the point is, you got to be excited. If you're going to be a physicist working on these ideas and they're speculative, you got to be excited in order to spend 10 years trying to figure out. It's not easy. It takes a long time, and therefore we shouldn't. I may make fun on one end by saying that we haven't made big progress, but that doesn't mean we shouldn't keep working. These ideas are interesting, and it's really important to point that out. But at the same time, during we came here, I discovered everyone had visuals, and I didn't have any. So I went on I went on the web and I asked for a visual. Can you have that visual I asked for? There we go.
There we go.
Okay. So what is this? This is one of Brian's ancestors who did this. This is probably the old, and I was inspired by you at art, but this is probably one of the oldest pieces of art in the world. It's 33,000 years old. It's from a cave in Germany. And I find it fascinating and inspiring because I look at that, it's the figure of a human with the head of a lion. And I try to figure, what was that artist? This is one of the first pieces of art humans have come up with. What was he or she trying to represent? And I think, well, maybe he was thinking, well, in my world, I live in a world with lions and with humans, but maybe out there somewhere there's a world with, it's possible to have lion humans, right?
Or just unified animal theory.
Yeah, and so, exactly. That's the point. That's my point. That it is fascinating and remarkable, and it's a testimony to human imagination that you can invent such things, but 33,000 years from now, it's possible that string theory will look like this. It's because it's a product of the human imagination, and we just don't know. It doesn't mean we shouldn't stop thinking about it, but we have to put it in perspective. We can come up with fascinating ideas, and we are. And some of them will be right, and a lot of them will be wrong. We just don't know.
Having all said that, I just want to amplify one point that we've already said. Again, general relativity, experimentally tested.
Yeah.
Quantum mechanics, experimentally tested. Each says the other is wrong. They're in conflict. We have really one theory at the moment that puts them together in a consistent way. So it's a touch more than just putting the line.
No, you're right. You're right. Ryan, I agree with you. I agree with you that it's better motivated than that. That doesn't say a lot, but it's certainly better motivated than that. I agree with you.
Shaman,
I just wanted to make
out here.
One comment, lest you all think that physics stopped being exciting in 1987 when Brian finished. So I got my PhD well after Brian. I'm still excited. But the main point is the following. When Kaluza and Klein had their great idea, 7 years apart, I guess, they put together one great idea, we could say in retrospect it was premature application of an idea. You could have the extra circle. You could get electromagnetism. So what? We now know the world has many other forces. There are many other particles they didn't know about. They had an elegant idea that was at best incomplete for many reasons, but that's the simplest one. We just know more about physics, and they didn't get everything. Mm-hmm. Now, one of the most exciting things to me that's actually happened in the last 20 years, and it certainly affects how we think about string theory, it's two different really strong pieces of experimental evidence. One is, in the late 1990s, we discovered what many of us would say is really strong evidence that we have a non-zero cosmological constant in our universe. This is a term that Einstein wrote down in his general theory of relativity equations to begin with. He realized it would give him the totally wrong answer if he didn't set it to 0, so he just set it to 0 by hand, which you can do, but it's not so elegant. And in fact, we seem to have found strong evidence, first through observations of distant supernovae, and now through a concordance of many different pieces of data, that this term is there. It's much smaller than expected, but in fact, it makes up something like 70%, 75% of the energy density in today's universe. I do not have a figure that illustrates the dark energy, but if you look in the room around you, it's around you. Okay? That's really exciting. We know this very concrete thing that most string theorists would have, frankly, found abhorrent in the mid-'80s. Another really exciting thing is...
But hold on to that for a second.
Yeah.
I mean, this cosmological constant idea from the perspective of Einstein trying to make a theory work out, okay, you're trying to measure everything in a room, but you can only see 95% of what's in the room. So to make it work out, because you know the confines of the room, you got 5%. You just have to go, well, it's this. We got all this stuff and this. Well, what's this? Well, don't ask me about this. It's just this. But within this sort of element of cosmological constant that you're talking about, these sort of mysteries that allow the mathematics to add up, can be an incredible amount of complexity that includes a lot of the phenomena that you're talking about.
But you got it actually wrong. We're 1%. What we've discovered about the universe, I mean, I do cosmology, and what's amazing is everything we see is just a bit of pollution. In a universe, I mean, you take away all the stars, all the galaxies, absolutely everything we see, the universe is essentially exactly the same. It's 99%, well, 30% dark matter, whose makeup we have good ideas about, but we don't know what it is, and 70% almost dark energy. Everything we see is irrelevant to the universe. It's really that scary. Okay.
So if there are not a lot of hidden dimensions, we are so friggin' alone. It's just not even comparable. Let's before we go, and we could go certainly another hour on this, certainly. What do you make of?
No, it's been a long day.
What do you make of this interesting union of artists and scientists attempting to describe the universe in this way, Linda? Is it a yearning by the artists and the culture at large that the scientists succeed, or is it a yearning for new material? I could make a painting out of some of that stuff. These crazy ideas are exciting. Let's work with that. What do you think?
I do think that during much of the century, between relativity theory and quantum mechanics, that neither quite so stimulating to the imagination of an artist as string theory or dark energy, dark matter. There are things happening in physics now, and I think popularizations of those things, which are very important, and I thank those of you who've written these wonderful books that make this material accessible, because that was certainly in the early 20th century. There was a real sense that the educated layperson should know something about science, and a great deal of popular science literature. And during this midsection of the century, I would say there's a sense suddenly that physics is really beyond me. There are certainly popularizations.
Yeah, you're right. There was a dip, and both Brian and I think were influenced by that. Einstein wrote popular books, and it was absolutely de rigueur if you were considered literate to have some understanding of natural philosophy. That evaporated, and there were some people like Carl Sagan, and I know that both Brian and I have been influenced, but the reason I write books now is because it was those books by Einstein and George Gamow that got me interested, but they inspire a generation of people, and one hopes that some people be inspired by the books you write.
And I think artists are deeply concerned with the nature of reality. And when new theories come along and this new way of thinking about matter and space and dimension, very stimulating. And as we've seen, the computer has really given artists incredible new tools for attempting to visualize this.
As artists that unified their work with Einstein were considered immediately to be in the avant-garde, that first superstring theory opera is definitely going to be on the fringe up at Lincoln Center. Brian, you said that when you were a grad student, you were so excited, and I detected a lot of that excitement in your opening presentation. You wouldn't say that you're not excited now.
No, I didn't mean to say that at all. I meant to say that the idea that we'd complete this theory in a year or two, which is what everyone sort of thought in the 1980s, that, in retrospect, well, it's certainly not true, and in retrospect, it was sort of premature to think that that would be possible. So yes, the excitement is still high. It's just as Lawrence is saying, there is a long road to walk, and it's not always that you're going to have a breakthrough after breakthrough after breakthrough. There are long periods where you're working in the dark and you just don't know if you're going to find anything.
And will the theory be confirmed in your lifetime, Brian?
I think it's possible, but I consider it unlikely. I consider it a huge long shot. But, there are many things that are a huge long shot that happen. So,
Comment, how about you? In your lifetime?
I'd be surprised.
Really?
Now, but the point is, and we really have to stress this, I always try to stress it, is physics is an experimental science. And what we really need, the theorists, what we really need, all of us would agree, is experiments. And every time we open a new window on the universe, we're surprised. The dark energy was, in general, a surprise. Some of us had ideas that it might be there. But that's why we're there. Well, I know it's too. But anyway, that's why we're so excited about the Large Hadron Collider. It's the first new window on a universe at a scale we've been waiting to see for so long. And I would be surprised if we weren't surprised, frankly. So,
That is the best thing, that something will happen there that's completely unexpected, you know?
And I mean, as to use sort of your collegiate work as an example, I mean, I'm happy with the 3 dimensions that we have, but the knowledge of other hidden dimensions suggests that I might someday graduate. And with that hope, I leave you all tonight. Thank you so much for being here.